So I can just do like a brief introduction, and then if questions come up, I'll be watching the chat and stuff. So if you're okay with questions during the talk, I'll just watch it and I can interrupt you if somebody chats or something like that.
Sure.
Okay, sounds good. Okay, so welcome everyone to our weekly condensed matter seminar. We're happy to have Stephen Wilson visiting us all the way from Santa Barbara. So Stephen has his PhD from the University of Tennessee, working with Pengcheng Dai, doing a lot of nice neutron scattering work on things like electron-doped cuprates. Then he moved on to a postdoc at Berkeley, working with Bob Bergeneau. Again, doing another nice series of neutron scattering investigations, this time of iron nictide superconductors. And then after Berkeley, he moved on to start his own lab at Boston College, where he took a very brave step of running a neutron scattering program looking at the perovskite iridates, which, if you're familiar with neutron scattering, is probably something you wouldn't decide to do as an assistant professor. In any case, that was a very successful, nice series of work. After that, he moved on to join the materials department at UCSB, where he's now associate director of the California Nanosystems Institute and co-director of the new NSF Quantum Foundry. His lab at UCSB is really a unique place where they push the boundaries of crystal growth for quantum materials and actually develop new methods for crystal growth to actively stabilize sort of metastable states. At the same time, he's really carrying out a lot of nice work in frustrated magnetism and things like that. And I think he's going to tell us about some new frustrated magnets and maybe potential quantum spin liquids today. So thanks, Stephen.
Great. Thanks for the nice introduction, Kemp. Yeah, so I mean, I'll get started and I'll just introduce the title of my talk, which is just, it's going to be, yes, touching a bit on frustrated magnetism and potential quantum disordered or quantum spin liquid states, as well as some unconventional phase behavior in a class of materials which are built, the chemical formula here is ARO2, where A is an alkali metal ion, R is a rare earth or lanthanide ion, and oxygen too. And so this is, for those of you who are sort of familiar with this type of chemical formula, it often invokes thinking about sort of what they call Della-Fossite-like materials, like you would think about in cathode systems. But it turns out, as I'll show you in a moment, there's a couple of different structure types that's stable in this class of materials. And I'll be talking about, two different structure types and why we think there's some interesting magnetism going on there. And yeah, so as Kemp mentioned, I've sort of moved to the dark side. I'm in the materials department here at UCSB. The talk will be sort of flavored a bit with, kind of what we'll say like the early end of materials development, right? Where we're sort of making the materials and then kind of doing some of the basic characterization and trying to motivate follow-on study with more advanced characterization techniques. So I'll be switching back and forth between a couple of different characterization techniques as we move through. So just, you've been warned. And yeah, so the work I'll be talking to you about today is supported by the US Department of Energy and the Neutron Scattering Directorate. Okay, great. So first, let me just acknowledge the people who did the work. So the vast majority of the work I'll be talking to you about today was done by a graduate student here in my group, Mitchell Bordelon, who's now graduating and moving on to Los Alamos as a postdoc. And so he's the one who's really been the driver for a lot of these projects that I'll be talking to you about. And he's also recently received, he's been collaborating a bit with a postdoc in my group, Paul Sard. And along the way, we've had the good fortune of collaborating with a lot of great people at both neutron sources, at the NIST and the SNS, but also some of my former colleagues at Boston College, Mike Graff, who's done some very nice low temperature AC susceptibility measurements for us on these compounds. And then at UCSB, it's really been crucial to trying to understand these systems. It's been Leon Valence's group and a lot of the great work by his graduate student, Chenjiao Liu, who's now graduating and moving on to a postdoc at Berkeley. Okay, So just as a quick overview, what I'm going to talk to you about is first, I'm going to just try to motivate the broader class of materials, which are this ARO2 type systems. And in particular, I'm going to talk to you about two different structural variants that occur in this class of materials. So one is a structural variant, which is sort of embodied by the sodium ytterbium O2 system. So the alkali metal is sodium, the rare earth site is ytterbium. And this system forms a layered triangular lattice structure, as they've shown here, where really if I was just to distill down the ytterbium magnetic sublattice of this material, this is sort of the magnetic exchange connectivity of the magnetic system up to the nearest neighbor J1 and next nearest neighbor J2. And the second, so this is an R3 bar M type structure. And so the second class of materials that I'll be talking to you about is lithium embodied by lithium ytterbium O2, where you can see the structure is dramatically different. And instead you have a connectivity between the ytterbium ions in this system that's what we call sort of a stretched diamond-like diamond lattice structure. And I'll talk more about that later. But again, this is just showing you the lattice connectivity between nearest neighbors, where J1 is in gray and J2 is the next nearest neighbor in orange, okay? And so I'll be talking to you about two different variants in each structure type. So first, we'll focus on, using this triangular lattice as a model to try and understand sort of the physics of what happens, the types of ground states that are realized when you put a ytterbium or a single hole F electron compound on the triangular lattice versus a single electron or cerium based F electron on that same triangular lattice. And then the second class, using this sort of distorted diamond lattice, we'll do the same thing. We'll take a look at the ytterbium variant, which is the single hole variant, and the cerium variant, which is the single electron variant. And I'll explain in the next slide what we mean by J effective 1/2 and what I mean by single hole and single electron magnetic ions in these systems. But first, before I do that, I just want to show you this nice kind of empirical, what they call radius ratio rule, which determines which structure type is selected as you move, as you basically take the chemical formula ARO2 and you change, well, sorry, more generally ARX2, where X in this case is the chalcogen ion, and R is the lanthanide ion, and A is the alkali ion. And if you look at the ratio of the radius of the rare earth ion over the sum of the alkali and chalcogen ions as a function of the lanthanide ion radius, then you can find these crossover points where this ratio changes across a critical value, and then the structure type that's stabilized switches. So here's just an example showing, going from the R3 bar M structure, which is the triangular lattice, to the I4 1 over AMD, or this is the stretched diamond-like lattice. So basically going from, if I was just looking at the line with ytterbium, right? If I start with sodium, then I can get the triangular lattice. But then if I want to switch, then I can switch the sodium to lithium and I'll get the diamond-like lattice, okay? And so this is nice, Mitchell is, he's a chemist at heart. So this is a nice radius ratio rule he came up with. And so I'll be talking to you about, so basically this sort of motivates why we chose the chemical formula we did to try and stabilize both the ytterbium and cerium-based compound for each of these two different lattice types, okay? So it just shows you why we have to swap out the A site as well if we're going to keep the oxide, the chalcogen site stuck on oxygen. Okay. Okay, so just for maybe the graduate students in attendance, if you haven't seen this sort of formalism before, basically why are we calling these J effective 1/2 moments? Okay, and so a good way to motivate just sort of the single ion physics in these compounds is first we can just think about ytterbium 3+ sitting on the rare earth site. And if ytterbium 3+, the magnetic shell is the 4F shell, and there's 13 electrons in there. And so the nice thing about rare earth ions is that Hund's rules actually work to the 0th order, right? You can use Hund's rules, and you can determine that this is going to give me a single hole in the shell with a J of 7/2, okay? And then the crystal field, or the interaction of the of this shell with the ligand field, or the oxygen ions in the system, will then lift this degeneracy of the 7/2 manifold. And basically, in particular, if you put it in what a D3D point group, which is a trigonally distorted oxygen octahedra, then you break this J7/2 manifold into 4 Kramer's doublets. Okay, so it's a Kramer's ion, so you're always going to have a doublet, right? Unless you break time reversal symmetry. And once we lift this degeneracy, what you're left with is a ground state doublet, okay? And the splitting between this ground state doublet and the first excited state doublet for an insulator can often be on the order of tens of millivolts, depending on the details of the system. But for rare earth ions, since the magnetic ions are so localized, you often have a very weak exchange interaction. And so when you think about the energy scale of magnetism in these systems, you're measuring at reasonably low temperatures, okay? So you're thinking about measuring at temperatures on the orders of a millivolt, right? And so if those temperatures are low enough, then effectively you've frozen out all of these higher excited states, and the system can be modeled as a J effective 1/2 system because you just have a twofold degeneracy. And so the same argument applies when you go from cerium 3+, from ytterbium 3+ to cerium 3+, okay, which is a 4F1 system, and which again, with Hund's rules, that gives me a J 5/2 state. And again, I put it in a D3D point group, which is relevant for the triangular lattice compounds I'm talking about. And again, you have, in this case, only 3 Kramer's doublets. And so, but again, the exchange interaction is much weaker. So when you're measuring low temperature properties, it should typically act as a good J effective 1/2 ion. Okay, so that was just some single ion background. So now if we're just thinking about looking at specific examples, I just want to first talk about the triangular lattice compounds. And so I'll be talking about 2 different variants. The first is the ytterbium variant, sodium ytterbium O2, and the second is potassium cerium O2, which is the single electron variant. Okay, so starting with it, so why are we interested in the triangular lattice? So this is, the triangular lattice is the canonical frustrated magnetic lattice. And so for those of you, who haven't thought about this before, if I was to decorate a triangular lattice with antiferromagnetically aligned spins, then there's sort of this obvious scenario that comes up where I can't decorate the entire triangle with anti-parallel spins, right? There's always going to be one site that's sort of frustrated relative to the other 2. And so classically, we know that this nature sort of solves this problem by acquiring what we call a 120-degree ground state, where each spin is rotated 120 degrees relative to its neighbor across the triangle. And so this is the classical ground state for Heisenberg's moments on a triangular lattice. And even this sort of classical picture has very interesting behavior. It means if you were to basically change magnetic field, you can drive what's known as a 1/3 magnetization plateau state, which is called, or the up-up-down state, where basically you get 2 spins on one sublattice that are point in one given direction, and the third points anti-parallel to those 2, and that's sort of a fluctuation-driven state. But then you can also add complexity by changing out of the sort of classical limit. You can start to think about decorating this lattice with quantum spins. So, for instance, spin 1/2 moments, where you can really enhance quantum fluctuations. And that was sort of an outstanding question for a long period of time. But I think the the picture now is that indeed 120-degree order is also predicted in the spin 1/2 limit. But then you can also think of other kind of complexity you can introduce into the magnetic subsystem by basically breaking the equivalence of these 3 different exchange pathways, right? So you could go to an anisotropic triangular lattice where you have, for instance, one exchange pathway J, and then 2 equivalent exchange pathways J prime, right? And so if in this sort of anisotropic triangular lattice, you can end up with non-collinear spin textures, as well as quite a rich magnetic phase diagram, as shown by here, this nice work by Chen. And so this is sort of a study of the rich magnetic ground states you can get in sort of the ordered regime, okay? But the triangular lattice also has a long history in people also exploring the potential for realizing an intrinsically quantum disordered regime, okay? So a ground state that's where quantum fluctuations destabilize any local order from forming. And so, for instance, predictions have been put forward if you were to add strong anisotropies into the model, so moving away from the Heisenberg limit, looking at strong Ising moments. Resonating valence bond states have been proposed and different forms of dimerization. And you can realize some of these by adding anisotropic exchange interactions, such as like Kitaev interactions, or if having ring exchange interactions, or even extended exchange, other types of extended exchange, to create a more highly frustrated magnetic state, which never realizes a long range ordered magnetic ground state. But actually realizing these types of sort of quantum ground states on a triangular lattice is actually, from the materials world, is actually kind of difficult, because really ideal manifestations of we'll say a quantum triangular lattice antiferromagnet are pretty rare. And the reason being is that you're always dealing with other competing interactions in real materials. So, and oftentimes when you think about creating a triangular lattice of magnetic ions, they're usually in a network of edge sharing, for instance, octahedra, in which case the magnetic ions get rather close together, and then you can induce things like metal-metal bonding. Other effects such as Ion-Teller distortions can basically break the degeneracy of the equivalent exchange pathways. So you can lead to sort of 1D exchange interactions. You can have anti-symmetric exchange interactions such as Tyloshinsky-Maria, which eventually lift the frustration at low enough temperatures. And then, of course, depending on the rate orbital extent of your magnetic ions, you can have extended exchange that can also serve to lift the frustration of the lattice. And so one of the reasons that recently rare earth oxides have on the triangular lattice have become of interest is because they can kind of get around a lot of these problems, meaning they're, extended exchange is typically quite weak, and rare earth ions are pretty versatile and fitting to a lot of different lattice types. So, and they actually are kind of nice, ideal moments to try and understand and model the ground states that you're getting. And so I'd say in the triangular lattice, one of the sort of big events was the material ytterbium, magnesium, gallium 04, which was proposed as a quantum spin liquid ground state. And so here's just a picture of the lattice of the material. So it's comprised of planes of ytterbium 3+ ions that are sitting in the center of oxygen octahedra, which are edge sharing. And then these are separated by magnesium and gallium spacer layers. So it's a 2-dimensional material. And the triangular lattice in the plane is sort of a perfect R3 bar M structure. And then, so basically measuring this system down to the lowest temperatures, there's no real order that's observed above 50 millikelvin. And if you look at inelastic neutron scattering, one of sort of the signatures that people look for is they look for the absence of well-defined spin wave modes or spin excitations. They look for signatures of spin-ons, for instance, if you were to have a quantum spin liquid state. And so there was some continuum spin dynamics observed in the system, which really drove a lot of follow-on research. But sort of one of the problems, or one of the open questions of this material was that it's the structure type it forms in is ytterbium iron 2 O4, right? And you can see that this chemical formula looks different than this one, right? And so the reason being is that this magnesium and gallium sites, they sit mixed on these interstitial layers. Okay, so you have like a large degree of alloy and charge disorder in the system, and so it's not completely obvious whether or not disorder drives the underlying phase behavior, or if it's the physics sort of inherent to a triangular lattice of ytterbium ions. Okay, and so that was some of the motivation for us to look into this material, so sodium ytterbium O2, because it realizes the same triangular lattice of ytterbium ions with R3 bar M symmetry. However, the sodium planes that space them basically lack a comparable level of alloy disorder, right? And so we can do neutron diffraction on this system, and we can show that the sodium sites are fully occupied within the planes, as well as the oxygen sites. And so this is sort of counterintuitive for people who've worked with a lot of sodium materials, because oftentimes you have sodium vacancies, but the ytterbium really loves to be 3+, and ytterbium oxide is very stable. So this system is a reasonably stable system. It doesn't really want to give up its sodium. Okay, it's not a good cathode system, for instance. Okay, and so we can also measure, basically another fact that we can get from the neutron scattering data that I've shown you here is that the actual distance between the ytterbium ions within the triangular lattice is about 3.34 angstroms, which is pretty close. It's for a number of rare earth oxides, especially ytterbium systems, I think this is sort of the closest ytterbium distance that I think we were able to dig up. I'm sure there's an exception, but it's close relative to some of the more well-studied materials. And the reason that's important is that means we should expect a reasonably enhanced magnetic exchange parameter along that exchange pathway. Okay, so the next thing we can do is we can look at the single ion properties of the system, and we should try and prove that indeed we have a well-separated ground state doublet relative to sort of the temperatures that we're working with. And so we can do inelastic neutron scattering measurements, and this is just a color map showing basically the energy transfer to the system as the neutron scatters versus as a function of the momentum transfer. And so, but we're talking about single ion physics, so you don't worry about the momentum transfer so much. Instead, you can just look at the energy levels. And what we see are 3 excitations, which if we do a one-dimensional cut, we can see these 3 modes. And these 3 modes are the excitations from the ground state doublet into the 3 excited state doublets, okay? So we can take the intensities of these and their relative energies, as well as fitting the magnetic susceptibility as a function of temperature, and we can solve and extract what the ground state doublet is, which we did. I guess the details of the actual ground state doublet are not so important for this particular slide, except to say that the first excited state is pretty far away. It's 33 millivolts away. So when I show you measurements, down below 50 Kelvin or so, we're pretty well into the J effective 1/2 regime. And as well, the other point is that these crystal field excitations are reasonably sharp, meaning they're limited by the resolution of the instrument, which just means that there's not an appreciable level or a measurable level of disorder from that the local ytterbium 3+ ion sees. Okay, so basically the crystal field seems pretty homogeneous in that regard. Okay, good. So now if we look at the magnetic susceptibility of this material, we can basically plot the inverse magnetic susceptibility as a function of temperature. And we can do a sort of a Curie-Weiss analysis, which looks a little weird. You see a deviation up here at high temperatures, because that's as you heat up above 100 Kelvin, you start to populate this this excited state doublet around 30 millivolts or so, and that changes obviously your magnetic susceptibility. But if you measure below 100 Kelvin, where you've sort of frozen out all of those excited state doublets, then you can get a reasonably good Curie-Weiss analysis. And we can get an exchange field, which is pretty high for a ytterbium system. It's about 10 Kelvin, okay? And it's antiferromagnetic in sign. And then we can look at lower temperatures, and this is AC susceptibility as a function of temperature. And the key is that you really don't see any features denoting any freezing or ordering in the system down to about 50 millikelvin. And the other key thing is that if we change the frequency of the AC probe, you don't really see any changes, which also helps to preclude any sort of unseen glassy freezing in the system, okay? And so, taking these 2 things together, we can ascribe what we call a frustration index to the system, which is a ratio of basically the mean field exchange that we're getting from the Curie-Weiss analysis divided by the lowest temperature that we've been able to measure the system. So basically an upper bound on when it could possibly order, which is 50 millikelvin, so that gives you about 200 Kelvin frustration index, which is really starting to imply that you're in a regime of sort of intrinsic quantum disorder in this material. And so we can look at it a bit more. And so here I've shown you the heat capacity of the same sodium ytterbium O2 system as a function of temperature. And we can remove the structural component, or the lattice or the phonon contribution to the heat capacity, and isolate the magnetic heat capacity by measuring a non-magnetic analog material, so sodium lutetium O2, which forms in the same structure. And then we can subtract the 2, and then we can just basically integrate the magnetic entropy, and it indeed approaches R log 2, which you would expect for a J effective 1/2 system, okay? So this tells you 2 things. First is that the J effective 1/2 model is correct in this temperature regime. And then the second thing is that basically by the time you've gotten down to 50 millikelvin, there's not really much entropy left to give, okay? You sort of like frozen the magnetic entropy out. So there's not like a hidden, even lower temperature ordering transition that we should expect. Okay, and so just as confirmation, we can do neutron diffraction on the material. I'm just showing you temperature subtracted data here, but just basically showing as we cool the system down, in this case, it's down to 300 millikelvin. We have other data showing down to 50 millikelvin. It's basically you don't see any magnetic Bragg peaks up here, or you don't see any correlated magnetic scattering up here. Okay. So this is basically just showing you that the system does not magnetically order as far as we can tell. And so where it gets interesting on this particular material, because other than just seeing nothing, you often want to have something to try and ascribe it to a model, and that requires usually seeing something. what we can do is we can look at the susceptibility as a function of field at low temperature. So this is 300 millikelvin. And what you find is that as you sweep field, you can find the susceptibility drops. And then eventually you have this sort of peak in the susceptibility that happens as you, will argue, is you cross a phase boundary. And then you enter what looks to be an ordered state where the susceptibility bottoms out, and then it starts coming back up, okay? And we can do, and so basically around 5 Tesla is where you're sort of in this ordered state. So we can do neutron diffraction under 5 Tesla, okay? And this is, again, this is a powder measurement. So the phase boundaries are not, let's say, sharp. It's more, you can envision it as a powder averaged phase boundary. So basically you can look at the neutron scattering under 5 Tesla, and we do indeed see magnetic peaks show up consistent with the formation of an ordered state. And we can solve the magnetic structure. And it turns out that the solution that works best is what has a propagation vector. It's a 2q structure, which is a third 0 plus a q equals 0 component. And this maps to this up-up-down collinear state that I mentioned earlier. Okay, so we apply a magnetic field, and then the best solution we get is inducing an up-up-down state where the ordered moment's about 1.4 μb per ytterbium ion. And there's 3 magnetic domains that should occur. I've just shown you the orientation for one of them, okay? And so why is this interesting or important? It's interesting because the up-up-down state's been studied for a long time. And so it's also, the effect of impurities on the up-up-down state's also been explored theoretically. And so from the Heisenberg model of the system, the up-up-down state, if you were to add impurities, in this case, here's a case for 5% non-magnetic impurities on the triangular lattice site. What it does is it basically destabilizes the up-up-down state and pushes it. It favors non-collinear states. So in particular, the addition of non-magnetic impurities seems theoretically, from this sort of Monte Carlo type of analysis, seems to favor sort of the what they call an umbrella state in field, okay? So in other words, the presence of disorder would tend to favor stabilizing a 120-degree state, okay? And so that makes that the up-up-down state sort of a useful fingerprint in our mind for basically saying, okay, the presence of chemical disorder in generating the disordered ground state under 0 field can be to reasonably good confidence ruled out, because the up-up-down state is still allowed to be stabilized, and it should be much more sensitive to the presence of chemical disorder in the system. Okay, so it was sort of a nice additional way to fingerprint the system. Okay, the other nice thing we can do is then we can take the inelastic scattering spectrum. So this is powder averaged inelastic scattering. So again, this is energy transfer as a function of momentum transfer. And so what we're doing is we're exciting, if it was an ordered system, spin wave excitations. But instead, what we see is about this third 0 wave vector, which is the 2-dimensional wave vector for 120-degree order. And we see this as sort of like mush of spectral weight. Okay, so we see these excitations that with no real like spin wave, like propagating modes that we can kind of model within this sort of powder average data. And there's quite a lot of spectral weight that's up here at finite energy transfers, okay? But what we can find is that when we apply a 5 Tesla field, what happens is that the spectral weight, these spin fluctuations, actually sort of condenses into the Bragg peaks of the up-up-down state. And then we also see sort of a well-defined band of magnetic excitations here, as well as some lower energy features. And so we can then take this spectrum that we've collected under 5 Tesla, and we can try and fit it using an XXZ Hamiltonian and a linear spin wave analysis, okay? And we can just do a powder average magnetic field. And this is stuff that Qinjiao and Leon Blentz did. And so basically by just doing this simple analysis with linear spin wave theory, we can get a reasonably good fit, really reasonably good match of the expected spectrum of magnetic fluctuations within the up-up-down state. And they can also utilize this subtle downturn here in this upper band to try and constrain what the deviation from Heisenberg exchange should be. And what they find is it has a slight XY anisotropy. So the XY exchange is 0.5 millivolt, and then JZ is about 0.45 millivolts. Okay, So we can get some sharper information.
Can I ask a question?
Yeah, sure.
So it's kind of hard for me to think about how it changes so much when you apply a magnetic field in a powder sample.
Yeah.
So does that already give you, the fact that it does that already give you some information about the zero field state? Like one way I could think it would change a lot is if you had like a singlet ground state that's basically doesn't care what direction you apply the field. Can you think about it in that way, or?
Yeah, I mean, it should. I see. It should say something. I mean, I agree that the fact that you have a sharp phase boundary, and this is sort of one of the things in my mind that's sort of been an enduring mystery, right? Why do we have a sharp phase boundary in something where the G tensor is reasonably anisotropic, right? So the GAB is, so the, in-plane G tensor is like roughly twice the out of plane. And yeah, it's a good question. It should tell us something about the quantum disorder ground state, the fact that it all wants to try and come up, basically polarize at once, at least within this particular system. But there have been, there are anisotropies in the single crystal studies, which have been done on slightly different systems, but that should have, roughly similar phase diagrams, which I'll talk about in a second. I would say that those are probably a sharper place to start than trying to infer anything deeper from the powder data, because we started looking at sodium ytterbium O2 and then we really focused on trying to make crystals of this because the oxide has just the cleaner physics. It's just larger crystal fields splitting, larger charge gap, everything, right? But it's just ytterbium oxide is just a bear to deal with. It's just hard to grow any crystals of it. So, but instead, if you go to sulfide or selenium or telluride, you can get single crystals, and then you can get sort of sharper phase diagrams. And there is an anisotropy between the field in plane and out of plane, and which is quite large. But for some reason, it's just not obvious in the powder. I don't fully understand it.
Thanks.
Yeah. Okay, good. So, basically, so the next step that sort of this was led by Leon Valence's group. Basically, you can look at all the asymmetry allowed terms in the magnetic Hamiltonian, and and they looked at both the allowed exchange within the plane. So this is within the triangular lattice, but also an interplane term, which they called H prime. And this is the basically for their spin wave model, they just used this first term, the two-dimensional XXE terms. Okay. And then basically further looking at the XXE terms under a magnetic field, then they can develop a magnetic phase diagram of the system. And sort of the predicted state under applied field is what they call this canted one phase, which is slightly different than the up-up-down state, meaning it's akin to an up-up-down state where all the spins have all been canted in the slightly and the out of, in the direction orthogonal to the direction that the moments are pointing, within the ideal up-up-down state. So, resolving the discrepancy between these two, it could be that the neutron scattering is just not our powder data is not sensitive enough to really resolve a subtle canting within the up-up-down state. Or it could be that other exchange interactions or quantum effects are, act to stabilize it a bit more, because this is sort of just the classical phase diagram. But nevertheless, this is the phase diagram they mapped out, and it sort of supports the experimental observation with this caveat here, with the slight canting that should occur. Good. And so, yeah, so this is kind of going back to the question that I was just talking about, so with the powder data, which is the best we can do with sodium ytterbium O2 right now, we can just plot an effective powder average phase diagram where you have the field versus temperature. And so the phase boundary here down at 300 millikelvin, or, basically measured down to 50 millikelvin at this point, shows that you have this transition, which is reasonably sharp from what seems to be sort of a quantum disordered state into this fluctuation-driven up-up-down state. We have some other data that I haven't shown you here because I don't want to go too much into the details, but suggesting that this upper field phase boundary here is actually first order, and that there should be, it seems to be a first ordered phase boundary into a non-collinear state. And this is consistent with some sort of parallel NMR measurements that have been done, where they also seem to see a change in the upper field phase boundary between, what they call state 2 and state 3 here. And it's also consistent with some expectations from numerical cluster field mean field studies, where there's predictions that at this upper field boundary, you can have a transition into what they call this V state, right? Where you kind of, the up down state destabilizes, but it's not completely disordered. Okay. Good. And so, yeah, I just want to say, one of the interesting things about this system in terms of quantum spin liquid behavior is that, these signs of quantum disorder are kind of ubiquitous across this alkali metal ytterbium X2 series, as long as it's in the triangular lattice structure. So for instance, if you change it to, if you look at sodium ytterbium sulfide, sodium ytterbium selenide, they all seem to have similar types of phase diagrams, with the energy scales just being pushed lower because the crystal field comes down and exchange parameters come down as well. And there's also been very nice work looking at NMR supporting the fact that the system doesn't order, that it has a sort of a fluctuating state down to the lowest temperatures they've measured, in this case, helium-3 temperatures. There's also MUSR data showing that you do have sort of persistent saturating fluctuations at low temperature in sodium ytterbium O2. And there's also other studies looking at other R-site variants. I forget if it's like maybe erbium or something. There's a few others where there's claiming that they may have similar phase diagrams as the ytterbium system. But one thing we wanted to look at was, okay, fine, let's look at the cerium compound. And so this is the same structure. We can do the same type of approach. We can do neutron diffraction, and we can show that the potassium and potassium and oxygen sites are fully occupied, which is important, especially for this system, because it doesn't really want to stay stable in air. So we have to be very careful. And the lattice stays more or less, is undistorted within resolution down to helium-3 temperatures. So it still has this perfect triangular lattice symmetry. So this system, we can do the same thing. All right, we can do a kind of Curie-Weiss analysis, and again, we can extract a mean field. In this case, the crystal field splitting is larger, so we can always, we get a good Curie-Weiss fit all the way up to 300 Kelvin. And so you get a mean field of about -7 Kelvin, antiferromagnetic. But then if we measure the heat capacity in the system, you can see it looks different, right? So basically, as we cool down, and this is again, we don't have a non-magnetic standard for this one, so we just do a Debye fit. But anyway, you see this like broadish peak, maybe suggesting the onset of short-range correlations, and then you see a clear kind of indication of a phase transition, which I marked at T star. Okay, and what initially got us interested in this is, I'll go back one slide. So this data was collected at 300 millikelvin, and we actually don't see any magnetic Bragg peaks here. So, we were looking at this, and, in principle, we were below this ordering transition temperature, and we weren't seeing magnetic Bragg peaks. So we're like, oh, what is this order? What's going on? That we're catching in heat capacity, but not in neutron scattering. And some of the interest was, there's been proposals for a long time of the possibility of having sort of multipolar order in cerium compounds. And the reason being is that you can have the cerium ion, the cerium 3+ ion in a D3D environment, which is the one we're talking about. It can acquire a ground state doublet, which is built from this J3 halves wave function, okay? And in that limit, the pseudospin operators can transform like dipoles and octopoles, or two dipoles and an octopole. So that it's sometimes called this dipole octopole doublet. And so in principle, this can result in sort of a hidden octopolar order that neutrons can't see, but maybe you can see as excitations that's somehow intertwined with the dipole sector. And so we were, first interested in this, like, oh, wow, maybe we have some sort of signatures of this. And here's just a phase diagram that's mapped out by Gong Cheng's group, for tuning the relative exchange parameters, whether or not you have a ferromagnetic dipole versus antiferromagnetic octopole, et cetera. Okay, so it's just a rich phase diagram that's been proposed. So we went and we did, again, the inelastic neutron scattering. This is the crystal field levels as a function. Basically, this is just a crystal field study. So looking at energy transfer as a function of momentum transfer. And we see, okay, so 3 excitations, okay? And the 3 excitations I won't go into. Suffice to say that you should only see 2. And this third mode is still a mystery to us, and it's nothing trivial. So I'm happy to discuss ideas for it, or if anybody has any questions about it later or now. But I can just say, it's not a trivial thing. We don't know its origin, but fortunately, there was a quantum chemistry group that somehow took an interest in this system and published a paper predicting what the crystal field level should be, and they should be exactly here and here. So we can actually still solve the crystal field Hamiltonian, and basically the dipole octapole doublet is not the ground state. It's actually fairly well separated. And for anyone who's looked at crystal field modes before, this is a huge crystal field splitting. So this is it's almost 120 millivolts to the first excited state, right? Which is completely above the single phonon cutoff for the system. So it's, for maybe the experts, this is quite unusual. But the key takeaway from this one is the dipole doublet is the ground state for this material, not the dipole octapole doublet. And in fact, we can do inelastic neutron scattering on the system at lower energies, and we see indications of what look to be well-defined spin wave excitations that are coming out of sort of the third zero type position, suggestive of a ground state where you have spin wave modes, and we're just sort of unable to resolve the magnetic Bragg scattering because of just the background's too high, and there's some limits on neutron powder diffraction in terms of the size of the ordered moment you can resolve. So basically, this spectrum differs from the continuum we see in sodium ytterbium O2. We think it's indicative of a very weak magnetic order that's below this T-star transition that we just can't resolve in our neutron diffraction measurements. And it's also consistent with recent reports on like potassium cerium sulfide, which is the sulfur analog of this system, where again, via muons, they actually see the onset of magnetic order at low temperature, at around the same temperatures. Okay, so in this case, the cerium analog seems to be a bit more boring. Just sort of, it's a frustrated compound, but it does seem to order, and it's, as a downside, it's actually much harder to work with. It's extremely air sensitive and harder to make chemically. Okay. So then we can switch gears, and I can introduce a bit this with the little time that I have left. These diamond lattice compounds. And so the way you can think about these systems, we've now just changed the, for instance, we've swapped out the sodium site with lithium, and that stabilizes a different structure type. And the best way to envision that is just to think of the magnetic ions on the ytterbium sublattice, and there's two different ytterbium sublattices. And so in a perfect diamond structure, they look like this. And this is sort of a well-known three-dimensionally frustrated material where you can have frustration due to these two equivalent J2 parameters as well as this J1, right? So an antiferromagnetic J2 will drive the system to be frustrated. And so we can imagine just taking this perfect diamond unit cell and just stretching it and making it a tetragonal cell. And if you stretch it far enough, then this J2 here moves up, and then eventually it becomes far enough that you can just ignore it. Okay, it becomes very weak. And then you can just think of the remaining J1 and J2 terms. Okay. All right, and so why is frustration on the diamond lattice interesting is that there's long been studies of the ideal diamond lattice, okay, where you can have a different way of forming a spin liquid state in sort of a classical form. You can have what's called a spiral spin liquid state, where basically there's a large degeneracy of possible Q vectors for the magnetism to order in. And so you can get this sort of spiral spin, what they call like a Fermi surface of degenerate spiral states. And there's been predictions and potential signatures of this in spinel systems, which are sort of like great materials for exploring diamond lattices. And then there's also predictions of having a quantum spiral spin liquid state with the people looking at, for instance, nickel rhodium 204, trying to explore that phenomena. Okay, but actually putting rare earth sites on a diamond lattice is pretty elusive. So there's not that many material manifestations where the rare earth ion actually wants to go in and form a diamond or diamond-like lattice. And so that was some of our motivation to look at this system. And so, okay, so here's just the material, and this is sort of the obligatory. We've done the neutron diffraction. The lithium and oxygen sites are fully occupied from the neutron diffraction, and the lattice remains more or less this I41 over AMD, like we expect it to be, down to 2 Kelvin, okay? So we can do the same thing. We can look at the crystal field levels, and all this is showing you is that we can solve the crystal field Hamiltonian. And again, it's a well-separated doublet with the first excited state around 45 millivolts. The details here are not super important for the remainder of the points I want to make, but just to show you that it is indeed a sort of J effective 1/2 regime. So for this system, then we can look at the magnetization. All right, so the susceptibility. And this is the inverse susceptibility. And again, we have to fit at low temperatures to get away from the thermally excited crystal field. But when we do so, we get an antiferromagnetic exchange interaction around -3 Kelvin. If you look at even lower temperatures, then what you find is that there's this cusp here where it freezes out, where you start to see the susceptibility turn over. And then at the very bottom end, you see there's sort of like this turnover here. Okay, so this data doesn't get low enough to really show much about this, but it suggests there might be something else going on at around 450 millikelvin. Okay. And so when we look a little bit more closely, we can look at heat capacity data, right? So this is heat capacity going down to dilution refrigerator temperatures. And so again, as you cool down the system, you can see that the magnetic heat capacity comes up. You start to form some short range correlations. And then you see this sharp peak here, which is the, which roughly coincides with the peak of the AC susceptibility data. But then as you cool down, there seems to be a second sort of transition down here at 450 millikelvin. Okay, so there's two different transitions. I call the first one here a TN1, the second one TN2. And then if you apply a magnetic field, more or less the second transition goes away. The first one sharpens up, and then basically the key takeaway is that this this 450 millikelvin transition, it's suppressed prior to reaching the polarized state of the system, which is about under 10 Tesla. Okay. So we did the neutron diffraction on this material, and we did it in the ordered state. So this is below TN2. So this is the ground state. And so 270 millikelvin, then the solution is actually an incommensurate magnetic structure. It's a helical state. And it's a helical state that's comprised of two different ytterbium sublattices propagating in a helix kind of along these dashed line directions, okay? And there's a relative phase between these two in the ordered state, okay? You can see they're basically one helix is sort of anti-parallel to the other as they rotate along, all right? But then what happens is when we heat up above TN2, sort of but below TN1, right? So in this intermediate state, this is at 830 millikelvin, then this perfectly ordered state doesn't really fit the diffraction data anymore. And Mitchell came up with a model that, the best fit he could come up with was basically he decided that these two helix, the relative phasing between these two helices becomes disordered, okay? And so it suggests that there's sort of this interesting intermediate disordered state that's below TN1 before you reach the ground state. So that's kind of an interesting manifestation and potentially driven by fluctuation effects on the ytterbium sublattice. And so what Mitchell did then is he then also applied a magnetic field, and he looked at what happens as you apply magnetic field in the system. What we find is that basically you still have a helical order, or the propagation vector locks in to a commensurate vector. So it goes from this 0.384 wave vector to a third 0 when you apply a 3 Tesla field. And so the phase diagram somewhat summarized here is a function of field and temperature. Basically, as you cool down at under 0 field, here's this what we call a disordered helix phase into this the ordered helix phase. And then as you apply a magnetic field, then it sort of locks into this third 0 type wave vector. And so what Leon Balentz and his student Chinchao Liu did is they fit this, they used this J1, J2 model to try and determine what the ground state should be. So they adapted their old model for a cubic diamond lattice. And it found that basically, yes, so indeed the model predicts a doubly degenerate spiral state with QQ0 and Q minus Q0. And so they built a phase diagram which basically which state you're in, antiferromagnetic with a Q equal to 0 versus ferromagnetic versus this incommensurate spiral state, is dependent on the ratio of J1 over J2. And so the nearest neighbor and next nearest neighbor exchange couplings. And so, in this regard, we could then basically back into, because since we know the propagation wave vector, it's actually we can actually calculate where we should be on this phase diagram, which is where J1 should be equal to 1.426 J2. Okay, so the model doesn't, this is sort of the minimal model. It doesn't capture everything, so it misses the phase angle between the moments on the two ytterbium sublattices, and it also obviously it doesn't predict this sort of intermediate state, okay, that we saw, this disordered helical state. So, to try and test the model further, we also decided, let's look at the single electron version, so sodium cerium O2, and just, as a a prelude is that, this is going to be, again, the cerium version is the boring version of the two. Okay, so we did the powder neutron diffraction. Again, the sodium and oxygen sites are fully occupied. That's important for this material as well because it's not very air stable. And the lattice remains what we think it is, down to 2 Kelvin. However, okay, so yeah, and so in the single ion physics, basically we can fit the crystal field of this one. We can establish the crystal field scheme. Again, in this case, it's cerium 3+. We only see 2 excitations. Those are the 2 we should see. So we can fit the ground state, and it's well separated. The first excited state is again quite high. It's at near 120 millielectron volts. And then if we look at susceptibility, in this case, we see this rather sharp cusp at 3.4 Kelvin, indicative of ordering. And it's slightly frustrated. If we look at the Curie-Weiss analysis, it's -8 Kelvin. So it's a little bit frustrated, but there seems to be a clear onset of magnetic order. And indeed, when we solve the magnetic structure, it acquires a conventional sort of collinear antiferromagnetic order ground state. So this Q = 0 propagation vector with the moments oriented along the long c-axis, okay? And the ordered moment's about a half a Bohr magneton, which this was done with a PowGen diffractometer, which is a time of flight source, which has much higher, better statistics for neutron diffraction than the neutron diffraction data we have on the potassium cerium O2. So it suggests that we were just sort of missing the ordered moment in the potassium cerium O2 system. Okay. But so then if we look at this proposed phase diagram, right, it starts to look a little weird, right? So we're here at the lithium ytterbium O2, okay? But then if for an antiferromagnetic state with Q = 0 order, that means the sodium cerium O2 should be out here, where J1 over J2 is now 4. Basically the ratio has jumped to almost a factor of 2. So, while this phase diagram does capture the known magnetic states, there's sort of an extreme sensitivity to changes in the lattice and the R side ion, right, that we don't fully understand yet. And it could be that other parameters are required to accurately model the system. The only other fully characterized magnetic ground state within this series of materials with the same structure is sodium neodymium O2 from Hashimoto et al., where it's known to be a ferromagnetic state. So, and that just involves flipping the sign of J1. Basically further developing this phase diagram is an ongoing thing, but there are many different variants that are known to be stable in this structure type that just, and we also know that from thermodynamic measurements that they order, but the order is just sort of uncharacterized. So these would be interesting to explore to try and further refine this phase diagram and what parameters are really essential to capture what's going on as these systems move across it. So yeah, okay, so I'm just going to quickly summarize here. So basically, if I were to look at single hole versus single electron systems, so this ytterbium 3+ versus the cerium 3+, in these two different lattice types, the key takeaway is the ytterbium 3+ systems seem to be a little special, right? They seem to be fostering these sort of enhanced fluctuation effects, where on the triangular lattice, it seems to be sort of intrinsic quantum disordered ground state, which have a lot of properties consistent with labeling it as a quantum spin liquid state, some of which I didn't get into. The unique thing about this system is that it does have this sort of field tunable phase, basically it's field tunable, meaning I can drive the system with a moderate magnetic field from a quantum disordered into a fluctuation ordered state and really explore that phase boundary more deeply. Whereas if I were to swap out the ytterbium with cerium, then I have a system that seems to acquire the likely 120-degree ordered ground state of that material. And on the stretch diamond lattice, again, the single hole system acquires this sort of highly frustrated sort of helical order. But it also seems to have this intermediate partial disordered phase that we're still working to understand. But in the cerium system, a cerium version of that, right, it's sort of just a vanilla sort of antiferromagnetic ordering, which is with a small degree of magnetic frustration. And it's sort of not the more interesting of the two. So I guess if I were to summarize future work that we're doing on these systems, basically one would say, what drives the quantum disordered state? What role does interlayer frustration play? We think that's important. Why is there such a difference between the ytterbium and cerium? And and single crystals are possible for systems that aren't the oxide, and so we're starting to work into that reason. And then yeah, for experts maybe like Kemp, I can try and ask him, why are there 3 excitations for cerium 3+ and D3D? And then on the Stretch diamond stuff, basically open questions are what's the nature of this intermediate disordered phase? Do quantum fluctuations play a role? And then, basically what terms are we missing from the Hamiltonian to really understand the evolution of the series, to try of the materials as we go across that phase diagram. And yeah, so I'll just leave my summary slide up just to motivate that, these rare earth oxides of the form ARO2 are interesting platforms for magnetic frustration. I think they can host some interesting ground states and phase behaviors, as I hopefully have illustrated. And then finally, I'll give a plug for the Quantum Foundry. It's a newly established NSF center. We really are specializing in material synthesis and characterization. So we're developing a lot of novel tools in-house here for both synthesis and characterization. And if you guys think that there's some way that we can collaborate, let us know. We're happy to try and work with you on either of those fronts. And with that, I'll thank you very much for your time.
All right, thanks a lot, Stephen. That was a nice survey of some interesting materials. So I'll open it up for questions right now. You can just go ahead and ask if you have any.
Sure thing. I'll stop sharing so I can see if anyone talks.
Okay, I'll get started with a quick one. So I guess maybe can you remind me in the spinel compounds, is there a significant difference in distances between the nearest and next nearest neighbor atoms? Because I'd be kind of surprised to see such strong next nearest neighbor exchanges in a rare earth system.
Yeah, there's a big difference in the distances, but the bond angles are different. So the nearest neighbor is 90 degree, but the next nearest neighbor is like closer to 180. So the feeling is that you can get some compensation. They can be of the same sort of footing.
But does that like good enough Kanamori stuff really apply for F electron exchanges?
Good enough Kanamori, or just the concept of having super exchange versus
I mean, just the concept of it being strong for 180 and weaker for 90 degree bonds. I don't know off the top of my head, so I haven't actually thought about those sorts of exchanges.
Yeah. I think the same principles apply in terms of the delocalization. Yeah. But I mean, it's weak, right? It's very weak in both cases.
Yeah. I see. Okay, so that makes a little bit more sense.
Kemp, do you have any ideas on the crystal field stuff? Have you dealt with any of that?
We're thinking a little bit about some things along those lines, but we haven't had anything crazy like that. I don't know. I mean, I guess one thing is I think cerium can be in a really different limit than ytterbium, right? Where in ytterbium, like the higher rare earths, it's really in this spin orbit coupled like J total limit. But in the lower rare earths, I think you start to get into things that are like more like transition metals. The orbitals become a little bit more extended, and I think you get
it's stronger coupling to the lattice.
Stronger coupling,
right? Yeah. I mean, it's just weird because Mitchell went back through and like there's in the literature, if you look, every time cerium 3+ is in a D3D environment, there's an extra mode. And everyone writes them off and they just ignore them in the fits or whatever. It's weird. Yeah, it's very weird. Yeah.
I guess then you can have a pretty valuable contribution if you can solve that.
If I can figure it out, yeah. I guess the latest one is cerium zirconate, right? So the pyrochloride. Yeah. There's an extra mode, and it's the same local field.
Yeah. So I guess another thing about these, these were a set of pretty nice rare earth compounds, and you kind of brought up this materials issues of things like disorder. So I guess, we're all, or I guess those of us who are thinking about these things are all thinking about magnets which have anisotropies in them, because anisotropies seem to make things interesting. But I think for a lot of these anisotropic models, disorder is a relevant term, right, in the renormalization group sense. So basically, any little bit of it completely washes out the spin liquid stuff. So I don't know, I guess just with the, kind of a consideration like that in mind, do you think from a materials perspective, there may be kind of better prospects to look for these things in transition metals or better prospects to look in rare earths? whereas like transition metals maybe give you higher energy scales, so you get a little bit more breathing room there. But
yeah, I mean, the problem with transition metals, you also get extended exchange, right? Which usually messes you up, and or you get things like Jahn-Teller or something that like I mean, in terms of like purity, I mean, like the sodium is a little bit of a misnomer, you know, in terms of like sodium ytterbium O2. It's as pure as anything. I mean, the sodium doesn't want to leave, right? You know, like I've had to like argue with people like sodium chloride, you know, it's pretty well established. So, I mean, so sodium ytterbium O2, it's pretty solid. The problem is we just can't get crystals of it. But it turns out that the sodium ytterbium sulfide, selenide, and telluride, you can do flux growth to get crystals of it. And people have started looking at anisotropies and things like that in those systems. And qualitatively, the phase diagrams look to be very similar. The energy scales come down. It's maybe not quite as clean, but it's still, I think you can get the same physics, would be my guess. So on that system, I think it's fine. I think if you're looking at systems like potassium, cerium O2, yeah, like never. I mean, we basically have to, I mean, well, cerium compounds in general, this is a problem, right? But like, yeah, I mean, these guys, I feel bad. They're, you know, they have to keep them under, you know, high vacuum, right? And they can't see air even for a little bit, right? It just completely destroys the system. So, so the cerium compounds are a real problem. But I think the systems, you know, sodium ytterbium X2, I think that's a promising way to have some like model spin liquid system.
Yeah, that seems like a clean system. I guess I just have it like a general, I don't know where it comes from, but when I think rare earth systems, I always think they're kind of a little messy, and for some reason. Okay, so what then? Okay, I'll ask another quick one. But do you have a sense of why is it that in the selenides and the sulfides you can actually produce crystals? Is it just that there's suitable fluxes that exist, or
suitable fluxes and just ytterbium oxide is super stable. Okay. So what happens, like even if you use flux, you know, you end up just blowing out all the sodium, and you get ytterbium oxide crystals. And it's just very hard to dissolve ytterbium oxide in anything.
I see.
You can use these. So I mean, like maybe someone who's a hydrothermal expert can probably figure out a way to do the oxide crystals. And I would love for someone to figure out how to do that. I think, but we're not tooled to do that because I think you have to do high pressure hydrothermal, and I'm not an expert in that, and I'm not really tooled to do it. But I think it could be done. But yeah, so the sulfide they do with wet chemistry, and then the selenide they just do with just selenium flux, more or less.
Yeah. Okay.
Yeah, but you do run the risk when you go to that region that you can have vacancies on the selenium sites, and people have to worry about that. Yeah.
I see.
But yeah, it's I have, you know, Mitchell, who's graduating now, like he spent quite a while trying to make crystals via all sorts of techniques.
Yeah, these things can be tough.
Right.
With this cerium, I don't know, maybe I'll give a chance if anybody wants to ask a question, because I'll just talk to you about materials, and I don't know.
Yeah, I'm kind of curious why the 3+ oxidation isn't a stable one, because +3 is usually it's usually a pretty stable valency in rare earth compounds. But why is the NaCeO2 air sensitive?
Typically, it's I think moisture and some combination of moisture and oxygen. Basically, it just blows out, turns into cerium oxide, right? I guess, and it kicks out the alkali metal. It's just I think you see this across a lot of cerium-based compounds, like cerium zirconate, for instance, another one. Even inside of the pyrochlor lattice, it wants to like decompose.
Yeah, for cerium, I don't think that the 3+ is necessarily.
Yeah, you have a lot. You have a couple other valences to try and go to, right? You can go to 4+. Yeah.
And also the lanthanide contraction happens just around cerium and the praseodymium. Do you think it's possible that the that it's actually a 3D electron system instead of 4F? Would
It's,
you be able to explain the extra crystal field?
oh, you're talking about the cerium system, whether or not there's a contribution from d electrons for the extra crystal field.
Yeah.
Yeah, that's a good question. I think we've discussed that before. I don't have a definitive answer for you yet. I would say that, the extent that we can measure, we can look at the form factor of the crystal field, and it seems to follow what we'd expect for a 4F electron, which is pretty different than what you'd expect for, d electrons. So, the form factor is just like the Fourier transform of the spin density.
Mm-hmm.
So neutrons are sensitive to that in terms of the momentum transfer. And so it seems to match best with a 4F electron.
Also, is there no extra crystal field observed for NaCO2, or was the energy didn't go above the two observed levels?
Yeah, we went to higher energies. Yeah, there's just the two. That one behaves normally. Yeah, for whatever. Yeah. So, like one idea, I don't know, that we've been trying to kick around is like maybe there's some sort of hidden stacking faults or something that somehow creates a slight, I don't know, you have to get to some pretty exotic scenarios to think about why you only get one extra mode instead of two.
Mm-hmm.
So one of those was stacking faults. Others have been things like you can get like dynamic Jahn-Teller effects, but those are usually pretty broad. And this is a pretty sharp mode. So yeah. I know, but yeah, you can. I'm happy. I can. If you send me an email, I'll let you know the number of systems that seem to have this extra mode. But it seems to be in a lot of materials. I don't know the reason though.
Yeah, so there's really no explanation of that. It's just kind of left out there.
Well, the issue is every time there's a one-off, like, someone solves a crystal field Hamiltonian, you've done this before probably. I mean, like there's always some weird thing, right? Like maybe there's some subtle shoulder or some other peak that people just say, well, that could be due to coupling to some phonon, like a vibronic excitation or something. And that's the most common one. But this is above but the unique thing about this potassium cerium 2 is that the first crystal field level is actually above the single phonon cutoff. It's really high energy. So it really kind of constrains some of these hand waving things. And we've also done, I didn't show the data, but we've done a whole series of rubidium, cerium, X2, and it's there in all of them: oxygen, sulfur, selenium, tellurium. And it's very systematic. So just trying to figure out exactly what's going on.
I wonder, are there any kind of optical measurements that can potentially couple to those modes?
Yeah, maybe. Yeah, I don't know.
You could probably see them with something like RIX at an image or something like that. I don't know if that would give you more information.
Yeah, it might. Yeah, that's a good point about RIX. Yeah. Yeah, that's not a bad idea.
How did you actually? Can I ask so the cerium? How did you deal, like from a materials perspective? Because I think. How do you clean that? Because I don't think it's quite difficult to buy. Cerium likes to have a lot of hydrides on it, right? So anhydrous cerium, like cerium oxide or anything like that you would try to purchase is usually a mess.
Yeah. Oh, shoot.
Do you start from the metal?
We start from. No, we don't start from the metal. We start from cerium oxide, and we use the alkali metal. So potassium is the metal. Or sodium metal. So we start from the oxides, and I guess, with the resolution of the chemical analysis that we can do in-house, which is, I guess, within like 1%, it seems to be good.
It seems to be good.
But yeah, because that's been brought up before, like somebody's like, how do you know you don't have like praseodymium in there or something? But yeah, as far as we can tell, there's not an appreciable amount of another like rare earth ion in our cerium. It would have to be quite a lot, in spectral weight terms, right, for the inelastic neutron scattering to pick it up.
Yeah.
But yeah, and it's like, making those materials is, I guess from the metal, You know, it's like making like little pipe bombs, I guess, you know, sealing.
Yes.
Yeah, it's something that only like chemists usually like to do.
Okay. Yeah, I'm not going to hold you here if people don't have more questions. We can wait a minute.
Yeah, sure. Well, thanks for the attention, everybody. It was great to give a seminar virtually.